Time for chapter number 5. Wallets. Rob, how you doing today?
I'm doing great. By the way, what's the show called again?
Oh, Breaking Down Bitcoin. Yes, this is Breaking Down Bitcoin. I'm Coin Guy Bride. Did I say that?
Yeah, you did. That's all right. I put the pressure on you. That's all good. No, hey,
good.
This is Rob here. Doing pretty well. So we're just going to get right into it because you guys should know or should have seen most of the episodes or before this, before we get to this one to kind of understand what we're going to be covering. But, as we're covering the Mastering Bitcoin book by Andreas Antonopoulos, which, by the way, what happened yesterday, Brian?
The man, special treat.
Yes.
My man, everybody's man.
My main man.
But the main man. He gave us a little shout out. He gave us a little spook, little confidence. Appreciate that, Andreas.
Tweet. You gave a little tweet and pointed to our videos.
Goes a long way.
Oh no.
That's kind of
huge.
Exciting. My phone didn't keep going bling, bling, bling. Just a subscriber. I was like, this is kind of like to go viral. This is kind of
it's like mini viral, mini crypto viral.
This is cool.
So kind of a big deal.
That was cool.
We have like 350 subscribers, so we're kind of a big deal. I mean, now what? We can retire with our YouTube, millions.
This is gonna be the worst episode. We're
full of ourselves now.
We're not. No. Yeah. That'll be the downfall of our show.
So.
Anyways, enough about us. More about the bigger picture, Bitcoin.
Yeah, we wanted to
the black hole. The event horizon.
Sorry to cut you off, but I know we wanted to cover the or really shout out to Programming Blockchain, Jimmy Song's seminar that will be hosted in, I believe, Santa Monica next week. I'm going to do just a quick little screen share of his website here, Programming Blockchain Interactive 2-Day Seminar, and
That's where we met.
Yep, it's where we met, and the rest is history. If you go to programmingblockchain.com, you can check out what his 2-day seminar covers, what you'll be required to know, some sample exercises, which you shouldn't be afraid of because honestly, he's going to go through them and help you understand them. But you definitely want to know a little bit of Python to get you started because it's pretty fast paced and for a 2-day schedule.
And I'd say if you could try to do a little bit of digging on our encryption, decryption, kind of just their public key, private key, the concepts, hashing, trapdoor functions. There's a lot of good, basic YouTube videos talking about colors of light, and Alice and Bob, and they try to do it with colors and just the concept because my strong point was not Python. I kind of did part of the class in Excel, which he thought was pretty impressive. That's cool.
A lot of the math and a lot of the equations
let me
done.
Excel.
And many other languages. It's mainly based on Python. Yeah. Python.
Yeah. But I mean, just knowing, kind of having a little bit of a math background, and I've just watching some videos on RSA and Diffie-Hellman. And I didn't really understand at the time, but it kind of was starting to click. The kind of the whole just trapdoor. You could kind of, it wasn't just gibberish. You couldn't do it, but you could understand it. But
oh yeah.
Anyways,
no. Exactly. Same here. And honestly, watching a lot of the videos after the fact cemented a lot of the things he was teaching. So it's definitely
slow. Things click like twice a week. Just slowly.
Exactly. Yeah. It was like a fire hose of information, and it was great.
It was.
And then after the fact, everything was cemented by especially by going through this book as well as watching many other videos. But I highly recommend it. You check it out, and actually kind of cool because we did a what's it called what do we want to call it, a little scavenger hunt last week.
Someone got our money. Did someone? I sent them money to an address to see if they could figure out where to get the private key. And I think who was our guy?
Was it Costin or Costin? We hope we're saying it correctly.
You send the money back to me, man. You don't have to do that. Like you deserve that. I mean, it was sitting in there for a while. I mean, I was like, are we bad teachers or people don't know this or?
Let's make sure that the
I haven't tried to do it. Yeah, so here's the last episode.
Yeah, I'm going to go ahead and make this a little bigger, but this is basically the private key, the with compressed private key that was required to unlock that with compressed public key or public address or address that
posted. I sent money to at the end.
Yep, exactly.
Yeah.
So it's right here, this one. Now there was also another private key, the non-compressed private key or uncompressed private key. I believe it's right here. This would not have worked. This would have gone to another address, the uncompressed address that was generated where the funds were not. So you had to know to look for the compressed, or at least guess and get lucky. And it took about
go ahead.
18 hours or so. It didn't take. It was less than a day by the time you got it.
What I did is the blockchain info, blockchain.info, and if you type it in right there on the little search bar, it'll pop up with a QR, and then you take your iOS app or with Mycelium, Jax, and do like cold storage. It's pretty cool. I didn't know public key. If you do a public key when you're trying to do a cold storage, like a retrieval, it'll tell you the value unspent on that address. So that was pretty cool in Mycelium. But yeah, then you would just pulled it out, grab the funds.
Yeah, no, it was pretty cool. It was pretty exciting when I saw it. I happened to refresh the page on blockchain.info and saw the transaction, and then Costin, posted it in the comments, which was awesome. I'm glad someone posted. It made us feel like, hey, someone was actually watching, and he actually, he sent it back because he said it was very cool,
actually
which is definitely not necessary.
Yeah. But anyways, yeah. So maybe we'll try to do something like that into this episode. I don't know. We'll see. We'll play it out.
Yep, we'll see how it goes.
Another surprise. So pay attention.
Yep, exactly. So now it looks like we want.
No, kidding.
Yeah, no, we want to jump into talking about the chapter on wallets and basically some of the terminology that's being used and help understand that.
Yeah, so man, I think if you're a big fan like Andreas, like I am, you've heard it before, and so other, he says it a lot, and it makes perfect sense. Two things: there's bad terminology in this space. One with the name Bitcoin, and this is just straight from the man Andreas, because the words of wisdom. Bitcoin is probably one of the worst ways you could describe what this stuff is, because you think coin, you think tangible. This stuff is it's abstract, it's the opposite, and which makes it kind of nice, as it's something you can agree upon, or standard weights and measures. They try to have copies of them, but now I think they're trying to agree like the pound is like the idea of so many atoms. But yeah, you're making something more abstract.
Oh, yeah,
it becomes more, you know what I'm saying? Yeah. It kind of concretes the idea. Other than that, so Bitcoin is, it's not tangible, it's abstract. And then wallets. I'm sorry guys, but you do not have Bitcoin in your wallets.
What? Wait.
No one has Bitcoins.
Wait.
Yeah. What?
I don't? Well, explain.
Let me explain for you guys.
Okay.
They're keys. It's a keychain, and it should make way more sense because
what's a keychain? The blockchain's a keychain, or the wallet is a keychain?
I'm so confused. What was my notes?
No, you're right. No, I just wanted. I'm playing devil's advocate.
Yeah, no. Your wallet is a keychain. So
okay.
My wallet, a keychain can. See, I have two apps, and I could load both Bitcoin on there. Right? I could only spend one. I can take a copy of a key. I can go to a key, go get a copy of a key, and I can have two copies of that key.
Yeah.
But I can only use one. So it's way, you can't make two copies of a wallet.
Right.
I can't copy my fiat. So the idea of a wallet, I think I killed that enough, but it's just not, you got to kind of slowly get at the masses a little bit, and you can't, get them oozed in so they can understand. But yeah, it's not how you want to think of it. And that'll help.
It's a way to manage. It's a way to manage your keys and addresses, and essentially, give you one place to store all that, all the keys to access the addresses on the blockchain in order to see what your balance, is. And think about it. You don't really actually have a balance somewhere in the blockchain. You essentially kind of do, but really, what a wallet software will do is it will take your key, turn that into the public address, find that address in the blockchain, and then be able to tell how much funds you have remaining by looking at like the most recent transaction, for example, that you received money in. That's probably going to be the the total amount that you have left, almost usually, or it'll have to go back to the beginning to when that address was first used and look at all the transactions and add them all up to see what the remaining balance would be. It's not actually just like a little box that says you have 5 Bitcoins left. And I think that's difficult for people to understand.
Yeah. There's like, you look at your bank account, you got your debits and credits and get your balance. There's every time you do a transaction, it's got to go down the chain, right? It's got to go look, add up all the all the points down. That's a good point. Other than that, good.
Yeah,
I guess I've thrown out there, I guess, to cover the basics. There's cold storage, which can be a paper wallet. There's I know there's we need to cover this stuff. Bitaddress.org, a good place to get Bitcoin paper wallets and some other stuff. Another type of cold storage. Oh, it's in my backpack back there. Trezor, I guess you can pull up the pictures of the Trezor. Or I guess or do we need to?
Yeah, no,
we'll do it. We'll do it.
Yep.
A Trezor or a Ledger Nano S. That's the two I have. I like the Ledger Nano S a little more because it's just a little more friendlier.
I'll put the picture up here. That is a Trezor.
When you do the whole Ethereum stuff on the Trezor, it makes you jump to my Ether wallet, and it kind of feels a little, what just happened? But they're both great. It's people are like saying, I hate when people they start doing verses. It's like Bitcoin versus Ethereum or Trezor. It's like they're both 99.99, and then this one's 99.9. It's just like
no.
And they're like slamming on each other because come on, we got to teach other people about Bitcoin. Let's not.
There's plenty of room for other currencies that have other purposes. There's plenty of room for other wallets, hardware wallets, or software wallets. There's plenty of room for multiple operating systems. Just like we have now. I mean, it creates competition. Competition's good.
Yeah, it's good. It's good, but it's like sometimes you're trying to compare which one's better. They're both. Unless you guys are getting interrogated every day and you got to worry about, you're fine. Anyways, and that with also, I want to say that the part about Bitcoin and Ethereum, for me, it's not a verse. This is from Andreas. He does the shark versus the lion. Have you seen that video?
Yeah, it's an awesome video. We should link that.
What's better in it? You put a shark and a lion in a cage, or they fight. Who's gonna win? It doesn't make sense because it depends on the conditions.
Yeah, and the shark.
So when you say
the lion can swim,
it's not a verse. It's which ones depends on the its surroundings. So just throwing that out there. That was a pet peeve of mine. But anyways, back to wallets.
Yeah. So wallets, as we put it here, is simply just a container that holds some big numbers and follows some instructions. I mean, that's the greatest way to put it in there. I mean, it's a file. It's literally the text file. I mean, it can be encrypted or whatever, but it's got your private keys that you just basically use to turn into a public key that can be then derived into an address to unlock and sign your transactions, unlock your funds and sign your transactions with. So essentially, that's all it is. It's not holding any sort of funds. And so what we want to move on to is probably the different types of wallets. Let me just go ahead and do screen share here so I can provide some visual aids. Back to the Trezor wallet. We're just going to go back to the beginning here. I threw this one in there just because I have to see it on Twitter, and I'm sure it's old, but it made me laugh. The hold the door from.
I just got that.
You're looking at it. I was looking at your face, and you're like,
slow.
I've never seen Game of Thrones. I don't know.
Yeah,
I just binged all 7 seasons of Game of Thrones in the past month, so I've never seen it, and now this just makes me laugh even more because it's in my recent memory. But anyways, basically there's 2 different types of wallets.
We probably don't use that first one very often.
Yes.
But so with this.
Yeah, the first one would being the I got to switch over to the picture. I realized that nobody could actually see the picture. So this is the picture that I was talking about.
Staring at me.
Yeah, exactly. We'll get this down someday. So anyways, two different types of wallets. I'm not sure if there's only two, but the two different types of wallets that we're going to be talking about are the non-deterministic or random wallet, as you can see here on this picture, which is just a collection of randomly generated keys. So imagine on your computer you have, or on your smartphone, you have a wallet. It's an old school wallet app, and it just happens to generate a brand new key completely randomly out of thin air, and keeps track of each one of those independently. Not very efficient because you have to back up every one of those keys, the entire key itself. And if you lose one of those, you lose any funds that are in there. There's no way to restore those keys back by backing up just one bit of information. You have to back up every piece of every key in that wallet.
This is very similar to people in passwords before the password manager, right?
Yes,
so
exactly.
This is, but you didn't get the chance to do the forgot me password. So this is why it was kind of the bad. It was a bad. Well, it wasn't bad. It was the best we had at the time. But this is the idea of that nothing was. Yeah, you won't understand until we explain the next. You explain the next one. But yeah, it's kind of like passwords, and people were trying to remember passwords.
Exactly. So yeah, there is no forgot my password option in Bitcoin. So unfortunately, so
you had to back it.
Exactly. So this is what we we're kind of showing last episode when we were generating a private key and a public key and an address based on that. Those were all non-deterministic or random wallets. They work great for one-time use, whatever. But if you're going to continue, you continually want to track and back up that private key, and you're going to hold Bitcoin in there and use it, you definitely don't want to use one of those type 0 or type O wallets. So now I'm going to go ahead and switch over to the next slide here, and you'll see the next type is the type 1, the deterministic or the seeded wallet. So it's not completely random. I mean, it's based off of a random bit of information that first generates a seed, but from that seed, imagine it to be a long string, like a 512-bit number, hexadecimal value. And that seed is then used to generate keys from that. And you can see here, it's just kind of a one chain. It's not really, there's no hierarchy here. It's just key 0, key 1, key 2, and key n. So there's just a sequence of keys derived from this. And then finally, there is the type 2, so the third type, is the HD or hierarchical deterministic wallet, which is essentially what you see here, a tree of keys generated from a single seed. So basically, we're going to go into how the seed is generated and how you can actually back up this seed easily. And once you actually back up this one seed, you have backed up every single child and grandchild and great-grandchild and so on and so forth to infinity. Yeah. Almost infinity.
Your honeypot and your addresses. I mean, it's okay in this sense because it's what.
Yes.
But yeah, you don't have to remember like the ones individually. I forgot something I just remembered when I first got into this space. I swear I thought they were hard drive wallets.
Yeah. Like, no, I thought the same thing. I thought HD. I thought HD meant hardware wallet initially because you'd see these treasures and all that.
Yeah, and I thought it was like a hard drive wallet.
Yeah, like exactly. HD wallet. Yeah, totally. I want an HD wallet. That's cool. But in reality,
hierarchical to what?
So that actually, I had to practice saying that word earlier. Hierarchical, deterministic. So
food pyramid, and there's a pattern to it. Yeah.
Yes, exactly. So you basically every child that is derived from the seed can be restored by just knowing the seed. However, you can't determine another child in the same branch by knowing the other private key or public key or anything. They're completely independent on their own, and they're completely random. They appear like every other what are they called, private key or public key that you could generate in type 0. They appear just like these, and there's no way to determine that they've been generated from a seed. So we'll skip over this. We'll just to cover the Trezor real quick, that it is a HD wallet in hardware. So it does the hierarchical deterministic tree that you see here, but it stores it in there.
Yeah, and just to throw it out there, most of the stuff, I almost guarantee everything your apps you're using are HD. If they ask you for those words, it's HD.
Exactly. So if you go into bitaddress.org, like we showed in the last episode, you're not getting this. You are getting random.
If you're probably a developer, if you're still using the first one, right?
Yeah.
I mean, because you're making your own keys and stuff.
Yep, exactly. So this is what the wallet software, like what Copay, Jax, insert wallet software here for your smartphone or even for the web. They actually they have their own engine, if you will, a mnemonic engine that follows these rules to generate a seed. So basically, the introduction of mnemonics allow you to generate a seed based on a list of words. In this case, it could be 6 and then another 6, 12 words. It could be 15 words. I think it goes all the way up to 24 words.
I guess so you can have a wallet. So the 12 and the 24 are really not anything special. I know.
Yeah. You can. Yeah, exactly. Like you can have anywhere up to 24 words, but it doesn't mean it makes it any more secure. It's just more difficult for people to guess at those 24 words. So there is some security there.
I could have a seed of 17 if I wanted to, right?
I'm not entirely sure. There may be a certain interval, only certain intervals that are supported. But we can check on that.
And I guess one I want to throw out here, I think we missed the idea of not using the same address. That's kind of the point of this.
Oh yeah, no, that's a very good point.
Right? Because your bank right now, your bank account, we all, your routing, your account number, it's using one address. All of our, that's one place. It ties you down to an identity. It's very easy to kind of watch from one point. So it needs to be recommended every time that you do a transaction, you use a new address. You kind of think it's kind of a pain, but it does it for you. But at first I was like, that's kind of a bummer because I can't easily keep track of things if I want to look on the blockchain. It keeps generating new addresses, but it really is. It wasn't that way. We all use the same address. It would be a bad system, or very
it would be scary. No, it would be because there would be a lot of risk involved. So, and there'd be a lot of privacy issues.
Yeah.
So this kind of doesn't remove any privacy issues, but it definitely decreases the chances.
It makes it easier to.
Yeah, and I can actually show kind of what we're talking about here. So say you have 5 Bitcoin in this key here, this child key KM0, and you wanted to send it to someone, but you didn't want to send everything because you usually don't. But you wanted to send one of those Bitcoin to Brian. You would send it to an address in a transaction, to Brian's address, and that 1 Bitcoin would go there. But then you always have to provide what's called a change address, which we're going to cover, I think, in the next chapter, transactions. So this change address is basically usually in the old, I'd say in the old style, or in the beginning, you would just send the money back to your address here, KM0.
Oh, is that how that worked? So it went back to the same address?
Yeah, I'm not saying it had to have, but you can, and you still can do that. It's completely valid. But it's a less private way because now they know that you own those coins. So instead of sending it back to yourself as change, those 4 Bitcoins, because you sent 1 to Brian, you'd actually send it to one of your children. Or even over here, it could be on this other branch if you really want it to be, but I'm not sure if it does that. But basically, think of it, it could pick any of these keys or even grandchildren, great-grandchildren, so on and so forth, and send the change to that address. Now, since this address is part of this tree, your wallet software will know that it exists and is able to scan all of these addresses on the blockchain, find out how much Bitcoin you have, and report it as one single balance. So
and a transaction always has to spend the full amount, right?
Exactly. So you can't. Yeah, go ahead.
No, yeah. So I guess if something was if something was 4 Bitcoin and as that example, you have to. Okay, I guess all your pieces them all together. You can't you always have to send more, a combination of all the, what am I trying to say? The paths, not the paths, but
Inputs.
the inputs. It has to always be, you can't cut it. You can't half an input. You got to.
Yes, exactly. So as I said earlier, if I want to send 5, or if I wanted to send 4 to Brian and I had 5 in this one address, I can't just send 4 to Brian.
You can't cut that, right? You can't cut that key.
The transaction's not valid without the change address, because it just doesn't make it needs to.
Yeah, I have to give a $5 bill to get one back.
Exactly.
I can't cut the dollar bill.
Exactly. So it's a little difficult to understand. We'll see probably in the transaction chapter more about this and how the change works. But essentially, in every transaction that your wallet creates, it creates an input. Your input is this key here, for example, that has your 5 Bitcoin. And then it creates at least 2 outputs. One of the outputs is going to be the destination that you want to send the money to. And then the second output will be your change address, which is usually one of your addresses in this tree. And that allows you to kind of hide where that money is going. It could look like, hey, this one of these is the change address, but which one's Brian's address and which one's the change?
I guess you don't always know. I mean, it's pretty obvious that that 2 outputs are from your, I guess, maybe not the newbie, but but you don't, like, I guess you really can't be certain of which one is the one intended for the other person, though, right?
Yes, the recipient, and which one is intended for the change.
Which one? Who am I sending? There's 2 going out. Which one?
You can make a guess, because a lot of transactions are usually even. Hey, I'm sending you 4, and my change is 1. So, okay. Yeah. But honestly, it's very difficult. And some wallet software.
I guess it's probably it's kind of probable to guess, but it's not. Yeah.
Yeah. Some blockchain explorers try to make a guess, but it can't always be right. So to go further into this, as we were explaining, the seed itself is usually, I'll just skip ahead, a 512-bit seed here. And you can see this is hexadecimal, 512 bits, and it's quite large and unruly, and you really don't want to store that. So a way to generate that seed is to use Mnemonic Words, which is just basically a list of words. In this case, we explained earlier, there's 12 words. Now, these 12 words weren't just made up by a human. It's actually randomly generated. They can be human-picked, but we're not a good source of randomness, so we would like to rely on the computer to do that. And so basically, the first step here is to generate the entropy, which is just randomness. Generate the randomness that the computer provides. Okay, 128-bit string, done. It runs it through a SHA-256 algorithm, which then turns it to a 256-bit string, and it takes the first 4 bits of that 256-bit string and tacks it on to the end of that random 128-bit string. So now you have a 128-bit plus a 4-bit string, and this kind of
took itself and gave a little back of it, a little part of it, right?
Yes, it took itself. It created a signature of itself through the SHA-256,
and it trimmed off a little piece of it. Yeah, and gave it back to it.
It cut off a piece of that signature and attached it back to itself. And exactly the reason is if you make one mistake in this, say you had to copy this entropy for some reason, this random string, and you made one letter mistake or number mistake, this checksum would not be valid, because if it SHA-256 this incorrect string, it is nearly impossible for the first 4 bits to be the same. Okay, so that's the whole purpose of a checksum. So the checksum would be invalid, and
that's really the point of that first step.
Yes. Yep, and you'll see this a few times more in Bitcoin. There's always a checksum attached to like the signatures or the transaction, and it's to check to make sure that the data wasn't corrupted in some way. So now that we have 100, exactly, when you're downloading, exactly, you want to be able to check the file integrity. So when you
has that ever happened? I sorry to digress, but
no.
Does that happen to people when they want to download something and the checksum's off? I guess, is that like a man in the middle of the or is that because of hacking?
Yeah, I'm sure there can be. Yeah, I mean hacking.
Right.
I mean, if you're downloading the source code from GitHub, it could be modified. It could be a fake GitHub page that you're downloading it from, and
so it's typically malintent stuff, right?
Yes.
It's not. Yeah, it's not like this. Okay.
Yeah, it could be.
I've never had one.
Definition errors. Mm-hmm. I'd say more so in the dial-up days than anything, but yeah, there definitely could be transmission errors, and there are dropped packets all the time, and these things have to be corrected, but it's usually pretty seamless to us. And I just apologize, I didn't have this slide up on the screen. I had Brian's face. So
oh, sorry, you're looking at me.
yeah, I put it back up. So
if we're wrong, let us know.
Yes,
you know.
yes, and so quickly, I'll just recap the list here. We generate the random 128 bits, SHA-256 it, attach it as a checksum to itself, and now we're at the point where we take the 132 bits. Remember, this is all random plus a checksum. We break it up into 12 segments of 11 bits each. So it kind of looks like this. This is 11 bits. 12 segments, 11 bits, 11 bits, 11 bits. Each one of these boxes corresponds with a word in a list. There's a word list. It's a BIP 39.
Yeah.
Yep, English word list of 2,048 words. So every 11-bit segment of this 12-bit segment or 12 segment list maps to a word. So this one happens to map to army. This one maps to van, defense, carry, jealous, true, so on and so forth. And you get this list. So this list actually can be translated back into binary, which will then be translated back to the entropy plus checksum, and you can take off the last 4 bits to get the entropy. So if we store just this, we will have a random number that can be derived from this list of words. So this list of words. Go ahead.
If you were to have abandon, it would literally be what 33 zeros, right?
Yeah.
It like happened. Okay.
Exactly.
I guess it just directly maps, right?
Exactly.
The words. Yeah.
Yep. And then there's the last word is a checksum as well, which I think is covered here. But let me go back. Let me make sure.
And we do have a question in the comments, but
okay, go ahead.
But it's for you. Is there a command? Is there any command show all addresses in a non-deterministic wallet? For example, Bitcoin CLI command.
No, that's a good question. I'm pretty sure there is something in there. I'll have to get it for you, and we can respond with that in a comment.
In the first kind of wallet, the non-deterministic wallet.
Non-deterministic. Well, that's what the Bitcoin node. A Bitcoin node is. So Bitcoin CLI is non-deterministic, I believe by default. So you should be able to generate multiple addresses.
Yeah, because nodes have wallets, right?
Yes. Yep. A node is a wallet. It's just not gonna have the mnemonics built in. It may have it, but I believe I read that by default it doesn't. So yeah, we'll get that answer for you. Good question.
Okay. I guess that's the point where you upgrade, right? Because it's a pain in the butt.
Exactly. So just to show you quickly, if the entropy can be anywhere from 120 to 256 bits, and again, entropy is just randomness. So it can have a random 128-bit to 256. This just shows you the size of the checksum increases with the number of bits that you're starting with. Here's the total size with the checksum, and then the total length of words in the the mnemonic length. So this is where the number comes from. So you asked about 17. Looks like it's invalid. So if you want to have a 12, 15, 18, 21, or 24, those are all valid mnemonic lengths. But 17 is not valid because it doesn't map to one of these.
Well, because the checksum is 4, 5, 6, 7, 8, right?
Yeah, exactly. Yeah, exactly.
There's no in between.
The reason for it all is math. So just take my word for it. So the answer to everything in Bitcoin is math. Now, the mnemonic to seed process. So, for example, we generated this mnemonic by randomly generating a number, splitting it up, mapping it to 12 words. Now we take these 12 words, literally mnemonic. It's always built in. That's the default.
Everybody uses this, right?
Yep.
I just learned that.
Yep. Every mnemonic seed has the word mnemonic in it as a X word or nth word. Yep, hidden in there. And then you can also add a salt, which is an optional passphrase. So you can write a whole sentence in there as a passphrase, and it will add more, what's it called, randomness to this seed. But by default, you don't have to put one in there, and it'll still be a random seed.
If your word, your treasure is jacked or it got tampered, that's a great feature to add an extra passphrase because you defeat the purpose. But I'm not
That's
saying
perfect. No, that's perfect. So yeah, if your Trezor gives you a list of 12 words, and you use those set of 12 words without an optional passphrase, and you lost your Trezor, someone could find it, somehow got your list of words.
Well,
somehow.
I mean, it was tampered on the way to you, you know.
Oh yeah, that too. But if someone stole it and happened to have your list of words, if they don't have your passphrase and you use one, they can't unlock it. So this is a mental
then again,
thing.
if you forget that word,
yeah.
you know. Yeah.
This is just this is using mnemonics with brain wallets, you know, which is like a memorized phrase that you don't ever write down.
It's a password, right? That's all it is.
Exactly. So anyways, once we build this new list with the mnemonic words, the word mnemonic plus our optional passphrase, it goes through this key stretching function. It's a PBKDF2 using HMAC SHA-5112. So basically, it's just a fancy way of saying it runs it. Yep. It takes it through a SHA-512 instead of a 256 algorithm, which means it outputs a 512-bit, hash, which is just a signature.
More math.
Yep. It's just a signature of all this data here. It takes it all and spits out 512 bits no matter what. But it does it 2,048 times.
Whoa, so, didn't see that part.
Yes. So not just once, 2,048 times. So it hashes
itself. That's a little
subtle. It hashes itself. Yeah, this should be big in red that it's not just once or twice. So this can take a while on a slow computer, I assume. Probably not that long, but I think this is part of the security here, is that it's not realistic that a computer can brute force this seed because of how many rounds that it has to go through. But anyway, so again, got another chart here. Basically what we do with those, that seed once we have it. So we take our words, we create a root seed. It could be either 128, 256, or 512 bits, apparently. But I believe most commonly 512. We then run it through the SHA-512, like I showed you earlier. Again, this is a one-way hash function. Just like everything in Bitcoin is a one-way hash function usually, so it cannot be reversed. And you can imagine this long string as two pieces, the left side and the right side, or the top and bottom in this picture. The left side goes and becomes the master private key, or lowercase m. And this is important later. The right side becomes the master chain code, which this is important later. So if you were to take this master private key, which is just this here, 5B5, 6C, 41, all this string right here, you can take this number, multiply it by G on the generator point, and doing the, what is it called, the elliptic curve multiplication, you will get your master public key from that. So this is...
So do that again. Say it again.
The same thing applies. So remember the last chapter, we get a private key, which is just a number. In this case, a 256-bit number. Okay.
Just a random. Yeah. Mm-hmm.
We take that, which is actually this part of the seed. It's the first left or top part of the seed, right?
Oh, I said uncompressed wallet.
Yes.
Yeah, it's uncompressed point. Yeah, X and Y point. Yeah. Mm-hmm.
No, this isn't X and Y. Just trust me on this. So the left side it goes to this point. Yeah. So the first part, which is the top of this picture here, the top number, is multiplied by G, the generator point, using elliptic curve multiplication to get your public key. So that's how your public key is determined non-deterministically. You just take a random number times G, and you get your public key, right?
A random number times G, and you get your public key. Yeah.
Yes. Yeah. Yep. It was a n time. What is it? N times G or K times G? That's what it is. K times G equals capital K, which is your public key. So this is the same process.
There was some kind of SHA-256 ripe MD ripe 160 to go from a
public.
Or is this that's
public key? No, that's your address.
Yes. Okay. Sorry.
So your public key is not your address. Remember, your public key is just a point on the elliptic curve, right? It's an XY coordinate. Then you run it through those SHA-256 and RIPE-MD 160 algorithms that we showed you in the last episode to get your address, your proper Bitcoin address. That's not we're not talking about the address here yet.
Okay. Okay. Yeah. So
We're just talking
okay,
about the.
public key, public address, two different things. Sorry.
Yep. Sorry. Yeah. That
Yeah.
is a good point though, because it is important to remember that keys are not addresses. The public key gets turned into an address by
But we're
running it
getting
through
there,
some
right? This is
hashing algorithms. Exactly. But then there's this new key or new portion called a master chain code. Okay. And in this next slide here, it looks like essentially the same thing. This is the same process, just showing that if you take a parent private key, you can do the same process to get the child private key. So we're just going to skip over that one. So this is how we extend a parent public key to create a child public key. And remember, the public key is what we create an address with. It is not the private key which unlocks the funds or unsigned signatures. This is the address number. So if I go back here, we have this number now, the public key, which is the parent or the master, capital M. We go to this graph. We start with the parent private key and the parent public key. We also get the parent chain code, which is this guy here, master chain code, and an index number, either 0 through, I believe, it's a 32-bit number, so 0 through whatever. We put all this together. We run it through a SHA-512 again, and we get what's the left side. We get a child private key and a child chain code and a child public key. So the same process. Nothing's really changed here. We're just taking this information here, running it through the algorithm again with an index number. You notice here, that's the new. That's what generates the new child. So index number 0 generates child 0. Index number 1 goes through the 512 hashing algorithm and spits out index number 1. So this basically, this number changing is what generates each child.
That's totally. Yeah, I mean that's all it takes, right?
That's all it takes, because you change one number before you hash it. Yes, you change one number before you run it through a SHA hash algorithm. It's going to change the entire string. It's going to look completely different.
That's the point of the hash, right?
That's like the point of the hash.
The epitome. And Rob, just remind the time.
No, we're good. We're good. Yeah, we'll wrap it up here in about 10 minutes or so.
Not this, yeah. But
yeah, I completely agree. The one-way hash function is irreversible, so that's the significance here. The left side again goes to become the child. The right side becomes the child chain code, which all that is just another number that gets used to generate some randomness in this.
So it's just add an index to just pump out these children.
Yep. Exactly. Index changes, pumps out children. Index changes, pumps out children. You can repeat the same process.
Easy enough, right? You don't need to do much to make a totally different one, right?
Exactly. So each parent key can generate 2 to the 31 children. Okay, so that's 2.1 billion.
2 to the 31
children. So this guy can generate 2 billion children. This guy
directly below him, or
directly below him.
Okay.
Directly below him. Now, each one of those children, each one of those 2 billion children, can have 2 billion more children, and each one of those 2 billion more children can have 2 billion more children. There is no limit. Now, of course, you're going to eventually wrap around and probably end up pointing at, private keys that already exist, collisions and all that. But realistically, you're not going to see that.
That'll be 3 universes from now, right? 3.
Yes, exactly.
Yeah.
Many universes away. Now it actually does generate 4 billion, but only the first 2 billion are used for what's called normal HD keys. Now the other 2 billion,
I guess they did just a part of the.
Yeah, they cut it in half. They said, hey, the first 2 billion are going to be normal keys. The second 2 billion are going to be what's called hardened keys, and I'll explain that here in a moment.
Yep.
So this is the process for hardened key. What is it? Derivation. It's the best way to say it.
Derivation.
Yep. So if you look at this, you'll notice the difference. See, this box disappears. Got the parent public key disappearing. So in this process, hardened is without the parent public key. Okay. Because with the parent public key in this algorithm, there's a chance that knowing some of this information over here and your parent key, you could actually unravel this and figure out what your parent private key is. So that is a huge, security risk. So that's the normal, what's called a normal HD, whereas the hardened is where they remove the public key from this hashing algorithm, don't provide it as input, and you're not able to reverse any of this or what's called reverse engineer any of this here by knowing the public key, because the public key is not used in the hashing, so it's not going to do you any good to know it. It still exists. The public key still exists. It's just not hashing it and getting its signature, because if that was to be exposed, if this parent public key were to be exposed, we could use that with some of this information over here. I don't remember exactly which ones it is.
Oh, I think I see
to determine what your parent private key is, which is not good.
This is how they can kind of group. They can start with I call it the grandfathers, and they can kind of branch. Like for a company could,
yes,
kind of address these set of keys to this, right?
Yep.
So like departmentalize down the chain.
Yes, and you'll notice the prime symbol here next to the 0, and it's gone here. So in the normal hard HD keys, there's no
What's
no
a prime
symbol.
0?
So now I don't know mathematically, but it's just to signify that this is a hardened index number.
Okay,
this is a hardened private key. This is a hardened chain code. So this is what that significance of that is. So you'll see that if you have like a Trezor, you'll see these zeros and these little prime symbols.
I gotcha.
So
I know what you're talking about. And I just realized this is the one we didn't talk about wallets and programming blockchain.
No, we didn't. We never got into this.
Yeah, that's why I'm like I'm struggling a little bit. But
yep, not a problem. And
no, Rob, you're great. Thank you. I just realized that.
So now the next page, we're going to show you how you actually denote or like record the path that you've gone down. So say we have this tree. Sorry, I'm going to jump way back. Say we have this tree. How do you know which path or which leg of this or branch of this tree you've gone down? How do you denote this guy? You need to know that this is the parent, and then it's this is the parent, and this is the seed. So there's actually a numbering system or a path system, if you want to call it that.
It's like if you lose your Trezor and then you got to get a new one, right? There's certain ones we decided, right?
Yes.
Arbitrarily.
So bit 44 specifies the structure as consisting of 5 predefined tree levels. So there's 5 tree levels, and you'll notice the prime symbol here to denote that it's using the hardened purpose, or the hardened first position, the hardened second position. So this would be like the grandfather, this would be the parent, this would be the child, this would be the child's child, and the child's child's child. So they decided, let's go ahead and pick one of these branches. In this case, they picked 44 in one of the BIPs. So
that's what.
No matter what, we're using a 44th branch in this tree for some reason. I believe that was just arbitrarily chosen. And they decided to set the purpose in here. So this is where 44 usually shows up. So the 44th child private key from the master private key.
I'm trying to pull it up on my Ether wallet and throw it in that PowerPoint so you can.
Cool.
So people can see.
That'd be cool. So now the next position is the coin type, and this can be 0 for Bitcoin. It can be 1 for testnet, Bitcoin testnet, or it could be 2 for Litecoin. And then I'm not sure what other coins are using it. I'm not sure if Ethereum's using it. I know Ethereum uses a similar structure, but I'm not sure if it's using 44 as its purpose. But anyway, then there's the account number. In this case, 0 is the main account. Then there's the change address and the address index. So these are just examples of paths. So if it's M/0, it's the first child private key from the master private key. Makes sense. If it's M00, it's the first. This is the first grandchild private key of the first child. Makes sense. Now, if it's M or 0 prime 0, then this is the first normal grandchild, because this one is not primed, of the first hardened child. Okay, that's the one without the public key using the hashing algorithm, and this happens to be one with the public key in the hash algorithm. So you can kind of mix and match them. You don't have to always go down the path of hardened or not. then there's this one, which is the first grandchild private key of the second child, so on and so forth. This is the first great-great-grandchild public key of the first great-grandchild of the 18th grandchild of the 24th child. So since these are zero-based, 23 is actually 24 because 0, 1, 2, 3, 4. Same thing here. But you'll notice the lowercase m and the uppercase m. That's not a mistake. The lowercase m is private key. The uppercase m is the public key. So there's actually two paths for every address, if you will.
Yeah. Now I couldn't. If I had my Trezor, I could try to get a screenshot. You see this. So if you have a Trezor and you put Ethereum on it, you'll go to myetherwallet.com, and it'll take you through a process, and then you get to a point, and it'll say Trezor is this HD path, and it'll say if you have which kind of wallet are you loading, and it'll put the path. That's what that. So that's what, like.
So
that's
here's
what
some more
means.
examples
like,
of the BIP44.
That's how we're
HD
going down the tree. We're going by this guy and then this guy. But you'll see that if you have a Trezor on they'll put Ethereum on it, or any ERC20 token.
So here's examples of the BIP44 HD wallet structures. I'm not going to read them all, but it always usually starts with the 44, and then 0002, 031, 14. So these are all the different branches. These are just the paths down the branch.
Mm-hmm.
So it always starts with 44. So just really quick, this one is the third. This is the third receiving public key. So this is like a public key that will receive money. Okay. Whereas if it has a 1 here, that denotes that it's a change address. So you can have a receiving address, and you can have a change address. So 0 is usually a receiving public key, and 1's usually a change address public key for the 4th Bitcoin account. So yeah, it's kind of difficult to show without seeing pictures of it and then paths and diagrams. But these actually mean something. So if you ever look at it and you ever wonder what this means, you can look it up at BIP44 just to understand what the structure means. But it's essentially just showing you what branch that this address is on. And that
they chose a path, and everybody agreed upon the path down the tree, right?
Exactly. So the last thing we'll show is just a quick, we always want to kind of show some Python or examples, some programming examples. I can just show a really fast one here. I don't have all the features of this library down, but I can show you that there's this library called Python Mnemonic, which actually generates mnemonic, word lists that can then be turned into a seed, which then can be used to derive, the master, public and private keys, and the children and grandchildren. So if you have Python, you can install this package. This is called Mnemonic. So I've imported Mnemonic.
Sounds like a wrapper.
Yeah. So from Mnemonic, import Mnemonic with capital M, and I've created a new variable called Pneumo equals Mnemonic English.
Couldn't have picked a better one.
Yeah, this is an example, so I just took it from there. So Pneumo equals Mnemonic English. That's the language, because we speak English. You can put other languages in there. It supports many other languages. You just have to have the word list for that language. So now I can just do a quick Pneumo dot. Wow, I spelled that wrong already. Pneumo. It's an easier variable. Let's just do generate.
I'm sorry, that's funny.
There we go. So we just generated a new mnemonic. This can actually be mapped, or actually
time divider generator point, right?
No, it would be turned into a seed, which we will do that. Let me just do A equals Pneumo. Sorry.
I'll stop talking.
That's all right. So now we've stored a new mnemonic in A. There it is. Basic resource, menu, boil, fat, whatever. It's always going to be that now because I stored that value in A. I can take that and then put Pneumo dot.
Oh, make your text a little bigger. Yeah, from the chat.
Sorry about that. I usually do that in the beginning. Is that making it bigger or not? No, it's not. So let me stop the share.
Ooh. Hey, Rob. We're good. Just chilling.
Okay. And now I'm back. Is it bigger now?
That's what she said. Oh, yeah, that's what she said.
No, I know what I did. I apologize. Let me fix this. 1 second.
There goes our PG rating.
Yeah. Jeez, way to go. I think I just crashed the terminal.
Yeah, now we gotta put
I just crashed the terminal. Almost. Wait, it's coming back. Sorry, I should have made it bigger in the beginning.
Yeah, so let's I'm gonna throw out I'm just gonna my favorite wallet, Mycelium. That's my big one to go to.
Okay.
And while you're getting ready, let me know. Mycelium. Jax, man, I was Jax. Jax is there's nothing else like Jax in it, but it's buggy. I think it's just where else do you get that kind of multi-sig on I guess I have an iOS. Well, Jax is a multi-platform, but I one time I pulled up one time. I said if I had 500 Bitcoins, I opened my app and I this. I couldn't do anything with it, but it gets a little buggy. But I trust that you back up your seed on Jax for sure because I upgraded it and it wiped it out one day, and I think I wrote down that seed. But anyways,
so my machine is choking because of me trying to resize my terminal window. So yeah, I blame Apple. We will skip that example, but basically what I could do with that mnemonic that I generated, I could then say, hey, turn this into a seed, and boom, it spit out a seed, a 512-bit seed, and then I could use that, continue to use that to derive, master and children of children, and this is necessary to do and useful to do programmatically because you can then build your own wallet and your own HD wallet using this library alone. You can have it generate keys all day and keep track of them. And it's just pretty cool that those tools are available and that easy to
and that's the Mnemonic and what is it called? Mnemonic in Python? Is that the tool?
It's just called Python-Mnemonic, but the actual to download it, if you have Python and you use pip packages, you just type in pip install Mnemonic.
And you can build your own wallet application with that tool. Yep,
exactly. Exactly. Yes, you can. It would be command line driven, but you can throw an interface on it, Flask, web interface, or even libraries available in almost every language, mainstream language, iOS, Java, you name it. So that way you can use it in Android and iOS apps and create your own simple wallet app, relying on libraries that have already been written to do all the secure, scary stuff. That's the
Gensar channel, Rob. You just
hey, well, I mean, if we're trying to teach people how to get into
I totally agree.
You gotta rely on libraries, especially if you don't want to be discouraged and hate your life. Now you can write your own library. That is awesome. If you want to go do that, learn the stuff, learn the lowest level you can and build from there. That's great. But if you want to develop something and feel like, I've actually accomplished something, start with the library, play with it, and then maybe look at the source code of that library and break it apart and learn from there. But if you're a pro, then yeah, build your own library. I'd say do that, but we're not going to go that deep. But anyways, yeah. So what I did was I did end up generating a mnemonic for you guys. I don't know if you could read it. Do you want to do this? Do you want to try something? So if you could read that mnemonic, at least one of you, I don't know if you can rewind it, pause it, and make out the words. We will use that mnemonic that was the first one that I generated in Python to actually generate a seed and generate an address. And we'll use the BIP44 path of 44 and all zeros with a 118 at the end. 118.
Is there M in there?
Yeah, it's M. It's either lowercase or it's lowercase for the private key. It's uppercase M for the public key. Now there's a website you can use to figure out what the key is. It is here, iancoleman.github.io/bip39. We'll throw it in the description here. And then we'll send a little prize to it. And if you can figure out how to
not right now, but I'd say within
the next
hour or two.
Yeah, and within the next hour or two, it'll be there. So
Refresh.
Definitely do your homework as fast as possible. If you find the address and there's nothing in it, just give it a little time, because we literally just created that mnemonic, and there's no way for us to know what address that was going to come out of.
And this is the mnemonic you pulled up on your Python that after you did dot generator, there was I remember something in there. Okay. So
it started with the word basic, and that's all I'll leave it at. So if you can find the rest of the words, throw it into a mnemonic code converter. Just Google mnemonic code converter. One's made by Ian Coleman. You can actually
and probably I don't want to give away too much hints, but I'm sure a lot of the cold storage apps are used. Is that a standard path?
Yeah, no, it is. So
we can find out. I guess
we're going to use the bit 44,
so,
and a lot
of
apps use bit 44 standard. So again, it's got to be the 44th, or M/44 with the prime symbol. The rest of it's all zeros, except for 118 at the end. We'll post it in the comments with it, the actual address. But you need to find this, and you need to find out how to get the funds out of there.
Yeah.
And if you do, yours. So yeah, that pretty much covers our chapter, I believe. We covered a lot about the wallets and HD wallets and mnemonics. And all this is going to add up to the next chapter, which is covering transactions and how to build transactions using information that we have learned in the past couple of chapters about keys, private keys, and public keys, addresses, and wallets, of course, because the transactions require all that information. It requires a private key to sign the transaction to make sure that it is you own the funds. It requires a public key because that public key needs to be turned into a Bitcoin address to send or receive to. So we'll definitely it'll definitely come together in the next chapter, in the next episode.
And one more thing I want to throw out.
Yep.
Everybody, you need to write your mnemonics down twice, right? Is that a safe way of doing it?
I would say so.
Yeah, I guess I'm thinking about it. I've only got written down one place. I've heard you write it down on 2 pieces of paper and you put someplace and separate them. So just in case your phone dies, you got 2 backups.
Oh yeah, for sure. And that's the beauty of this that I don't know if we touched on, is that you get that mnemonic phrase and you lose your phone dies. You simply just get that. Yeah, you lose your treasure. You just get that phrase and enter it into any bit 44 supported wallet or new treasure, and it will then be able to generate all the same addresses, all the same children.
That's why you write down those words. Yes. You write down those words.
No matter how far you've gone down those tree branches to generate addresses, it could be billions. It's more than likely not going to be billions, but it could be billions. Your wallet software will be able to regenerate those, search for them on the blockchain, and recover your funds. So that's the importance there. So don't use randomly generated wallets. Use non-deterministic hierarchical
hard drive wallets.
HD wallets. Yes, exactly. All right. Well, I think that pretty much covers everything.
We beat that one.
Yeah.
So wait, transactions next time?
Yep, we're going to do transactions chapter 6. So we'll see you guys probably next week. And thanks for joining us. Go ahead and like, subscribe. We have a tip, address as well if you feel friendly. But thank you for joining us.
If you want to tear us apart in the comments, like we totally screwed some point up, please do. I want it. Let's help us all understand this. So
exactly. Yes, please do. We accept all input because we literally are reading this week. I mean, I'm only this far in the book, as far as what we just read up to, which is not even halfway for the wallets.
We'll probably have to read it again later.
Yeah, this is how much we know, besides what Jimmy tells us.
Yeah.
So yeah, it's been fun. All right, guys.
Break down Bitcoin. All right, guys. Thank you.
All right. Later.